Hello everyone. This video is entitled Covalent Bonding. In this lecture, I'll be introducing the concept of intermolecular forces, and I'll discuss how these forces impact our everyday lives. More specifically, I'll be focusing on the van der Waals forces, which include dipole-dipole interactions, London dispersion forces, and hydrogen bonding. If you have not yet watched my video on electronegativity, it is recommended that you do so first to fully understand this material. You can find a link to that video in the description below. Okay, let's get started. Let's start by reviewing a few basic ideas relating to covalent bonding. So, we know of course that covalent bonds usually occur when two or more nonmetals bond with one another. But it's also crucial to remember that there are exceptions. As we discussed in past lectures, it is possible for metals and nonmetals to form covalent bonds as long as the electronegativity difference between the two elements is less than 1.7. Recall that a difference in electronegativity between 0 and 0.4 creates a nonpolar covalent bond, while a difference between 0.5 and 1.6 creates a polar covalent bond. A covalent bond, oftentimes referred to as a molecular bond, involves the sharing of electron pairs between atoms. These shared electrons are called bonding pairs. Unlike in ionic bonding, where atoms transfer electrons to reach stable states, in covalent bonding, electrons are shared to create a stable balance of attractive and repulsive forces between atoms and within atoms. So a covalent bond is called a molecular bond because a single covalent compound is called a molecule. It's very important to take note that an ionic compound can never be called a molecule. The word molecule is exclusive to covalent compounds. If you're describing a single ionic compound, you would refer to it as a formula unit. So molecule for covalent compounds and formula unit for ionic compounds. Now, in a molecule, a single bond occurs when two atoms share one pair of electrons, as this image to the right illustrates. If a compound has a pair of electrons that is not shared, they are known as a lone pair. So this ammonia compound illustrates a lone pair beneath the nitrogen. Below you can see the creation of a bond between two chlorine atoms, and the expression of a bonding pair and many non-bonding or lone pairs. At times, two atoms need to share more than one pair of electrons to reach a level of stability. A double bond involves the sharing of two pairs of electrons, such as in the case of this oxygen molecule, O2. Note that multiple bonds are expressed by using more lines between the atoms. A triple bond involves the sharing of three pairs of electrons between the atoms, such as in the case of this nitrogen molecule, N2, again expressed with multiple lines. In the last slide, I showed a few examples of compounds formed with atoms of the same element. When atoms of the same element share their electrons equally with one another, they form what is called a pure covalent bond. Now, of course, if you were to take the difference in electronegativity of these two atoms, it would equal to 0, making the bond between them completely nonpolar. But not every nonpolar bond is a pure covalent bond. There are atoms with very close electronegativities that share their electrons almost equally. An example of this would be a bond between carbon and hydrogen. The electronegativity difference between them is 0.4, making the bond nonpolar. When compounds consist of only two atoms with the same element, they are considered diatomic molecules. There are only 7 known diatomic molecules in existence. These diatomic molecules can best be remembered with the use of an acronym, Hoberfinkel, which is spelt Hoberfinkel. Hoberfinkel. Intramolecular versus intermolecular force. Before we go any further with this lecture, it is crucial that you understand the difference between an intramolecular and an intermolecular force. An intramolecular force occurs within the atoms of a compound. These are attractive forces between atoms or ions that form either covalent bonds or ionic bonds. These are very strong types of forces. An intermolecular force occurs between two or more molecules. And yes, I said molecules because this only occurs between covalent compounds. This force causes molecules to cluster closer together and potentially form solid, orderly lattice-like structures. These types of forces are weak. In the next few slides, I will describe the importance of intermolecular forces. The properties of molecular compounds cannot be simply explained by covalent bonds. Many covalent compounds are nonpolar by nature, and so how or why do they cluster together? Because these compounds do not have electrostatic attractions to keep them together, forces must exist between the molecules, or many would be gaseous at room temperature. The intermolecular forces that exist between molecules and govern their behavior are called van der Waals forces. Dutch physicist Jonas Dietrich van der Waals was the first to describe these intermolecular forces in 1873. These forces have since been categorized into three types: dipole-dipole interactions, London dispersion forces, and hydrogen bonding. As we've discussed in previous lectures, the unequal sharing of electrons within a molecule causes slight charges on either side of the compound, known as dipoles. These dipoles are caused by polar covalent bonds within the compound. When two polar molecules get close enough to one another, the positive end of one molecule is attracted to the negative end of the other, and vice versa. This image here shows the interaction of dipoles on two different water molecules. These forces are only important when the molecules are close enough to one another. If they aren't, they will not interact. The second intermolecular force is the London dispersion force. The London dispersion force is an expansion on van der Waals' 19th century theory. Proposed by German physicist Fritz London in 1930, the London dispersion force describes the behavior of electrons in nonpolar molecules. Electrons tend to stay as far apart from one another in an atom as possible due to the repulsion of their like charges. However, occasionally the electrons within an orbital are attracted to the nucleus of a nearby atom and wind up on the same side as shown in this helium atom. The instant both orbiting electrons move to one side of the atom, it exhibits polar characteristics. With an excess of electrons on one side and a shortage on the other, opposite dipoles are generated. This image here shows how a London dispersion force is created. The nucleus of helium atom 1 attracts the electrons of helium atom 2 and draws them to one side. This instantaneous dipole created in helium atom 2 causes the electrons in helium atom 1 to be repelled to one side, and this causes the dipole in helium atom 1. The dipole created is called an induced dipole, and so helium atom 2 would have an instantaneous dipole that occurs with the drawing of electrons by a nucleus, and an induced dipole would occur in helium atom 1 with the repulsion of electrons by the instantaneous dipole. And so again, this would be called an induced dipole. And so even in nonpolar molecules, you have the spontaneous formation of dipoles that causes these atoms to be attracted to one another. It is important to note, though, that since electrons move quickly, these dipoles only last for a fraction of a second, but they are continuously generated, which keeps these molecules together. It is because of London dispersion force that nonpolar olive oil is able to stay in liquid form, Without these instantaneous and induced dipoles, the molecules would have no reason to stay together, and would separate from one another into gaseous form. London dispersion forces are present in all molecules and unbonded atoms, whether they are polar or nonpolar. The tendency of an electron cloud in an atom or molecule to distort like we saw in helium is called polarizability. High polarizability creates a strong dispersion force, and low polarizability creates a weak dispersion force. The polarizability of an atom or molecule increases with increased molecular weight. Larger atoms or molecules have larger electron clouds, which increases the likelihood of them polarizing. As you can see in the table below, the greater the molecular weight of a compound, the greater its boiling point, meaning the harder it is to separate the molecules due to their polarizability. The shapes of molecules also affects the magnitudes of the dispersion forces between them. This image shows how the shape of molecules affects their ability to polarize and attract other molecules. Even though these compounds are composed of the same number and type of atoms, their ability to generate dispersion forces varies quite a bit. An elongated molecular shape, as shown to the bottom left, provides a greater surface area available for intermolecular contact between molecules. The more points of contact, the greater the likelihood for the creation of strong dispersion forces, strengthening the attraction between molecules. The more compact shapes offer smaller surface areas available for intermolecular contact, and, therefore, weaker or fewer dispersion forces. So, to review, London dispersion forces occur due to an uneven distribution of electrons, which create temporary dipoles. This uneven electron distribution increases with polarizability, which itself increases with molecular size and intermolecular contact area. This graphic illustrates the formation of these temporary dipoles. The electrons in the helium atom on the right are attracted to the second helium atom's nucleus. As those electrons move towards the second helium atom, they repel the atom's electrons. This causes both helium atoms to form temporary dipoles. These dipoles interact with one another, which causes these helium atoms to connect in a way these nonpolar atoms would otherwise not. Now, I'm sure at this point, some of you have been wondering why this effect is called a dispersion force. Well, Fritz London called his theory a dispersion force due to the meaning of the word dispersion in physics. The word dispersion relates to the change in the quantity of energy of electrons from their original stable state within an atom when they move to one side. The third van der Waals force is hydrogen bonding. Although this force is titled as a bond, it is not. Hydrogen bonding is not a bond, it's a force. This intramolecular force is referred to as a bond due to its strength and the fact that hydrogens must be bonded to the molecules that are interacting with one another. Hydrogen bonds are the strongest of the intermolecular forces. In fact, hydrogen bonds are just three very strong dipole-dipole interactions that exist between the partial positive of a hydrogen atom in one molecule and the partial negative charge on either nitrogen or oxygen or fluorine in another molecule. Only these three elements can perform hydrogen bonding due to their high electronegativity values. This force explains the unusual properties of water, its high melting and boiling points, and its ability to dissolve many substances. The image in the top right corner shows hydrogen bonding, represented by dotted lines, occurring between the hydrogen and oxygen atoms in different water molecules. These intermolecular attractions keep water molecules tightly connected to one another. It is for this reason that water molecules are very hard to separate, hence water's high melting and boiling points. The image beneath shows the intricate arrangements these water molecules can form as a result of hydrogen bonding. Snowflakes are just very large frozen displays of these arrangements. Water is the only substance that exists naturally in three states, solid, liquid, and gas, on Earth. This is of course due to the amazing properties of water as a result of hydrogen bonding. This graph shows the boiling points of molecules as a relationship of molecular size and temperature. The red line represents polar molecules and the blue line represents nonpolar molecules. As you can see, although water is one of the smallest compounds displayed here, it has the highest boiling point. Because water molecules are bound together so tightly, it requires an incredible amount of energy to separate them from one another. To put water's boiling point into perspective, water transitions from solid to liquid, it melts, at a temperature that is higher than the boiling points of all the other compounds on this graph, whether they are polar or nonpolar. This really brings into focus how strong these special dipole-dipole interactions are. Surface tension is another amazing property brought on by water's hydrogen bonding. Surface tension results from the force of attraction experienced by the molecules on the surface of a liquid. Each water molecule can potentially form 4 hydrogen bonds with its surrounding water molecules. Due to the hydrogen bonding, insects such as the water strider, that is denser than water, can move across the surface without sinking. It also happens to be the reason why belly flops really hurt. Water also has the incredible ability to expand upon freezing, which again is brought on by hydrogen bonding. The expansion is due to gaps created between the water molecules when they arrange themselves into rigid ice crystals. This is why ice water is less dense than liquid water, allowing it to float. Very few substances have solid forms that are less dense than their liquid forms. And with this slide, I conclude this package and this lecture. I hope you understood everything I discussed today. Thank you for listening. All the best.